Next, to get an introduction. Torsional vibration is an angular vibration of an object, commonly a shaft, along its axis of rotation. Torsional vibration is often a constant in a power transmission system using rotating shafts or couplings, where it can cause failures if not controlled. A second effect of torsional vibration applies to passenger car. Torsional vibration can lead to a seat vibration or noise at certain speed, but both reduces the comfort. In ideal power generation or transmission system using rotational parts, not only the torques applied or reacted are smooth, leading to constant speed, but also the rotating plane where the power is generated or input. The plane is taken out, which means output are the same. In reality, this is not the case. The torque generated may not be smooth. Example, internal combustion engine or the components being driven may not react to the torque smoothly. And the power generating plane is normally at a distance to the power taken off plane. Also, the components transmitting the torque can generate non-smooth or alternating torques. Wound gears, mislaying shaft. Because of no material can be infinitely stiff, these alternating torques applied at some distance on the shaft cause twisting vibration about the axis of rotation. In experiment, they have done one experiment based on single degree of freedom torsional vibration.
Assalamualaikum. I want to explain about the procedure of torsion vibration system. Okay, for the first experiment, the shaft is fit at the one end, followed by the eccentric mass. The eccentric mass is clamped tightly, another end of the shaft is fit. Okay, adjust the clamp force in order to allow an isolation of the steel disc to tight, make prohibit the vibration motion of the steel disc. Okay, for the third procedure, to load a feet at each of side of the eccentric mass. Make sure the load is fit. And the fourth procedure, the astrometer is attached to one load. Okay, make sure the direction of the astrometer is correct. Located is upright by the following the arrow sign. Okay. After that, the results are recorded and interpreted to fulfill the objectives. Okay, for the experiment 2, for the step 2, is repeated by replacing the eccentric mass to the test fit.
Okay, let's see how do we do our result. In our result, we use NIDAQ max. We click to NIDAQ and make sure our configuration is at acceleration. And the sensitivity is adjusted to 97.9, and we have a continuous sample. And then we run the whole program, and after a while stop it, and we click save. After saving, let's go to our Daisy Lab setup and layout. This is our layout, a simple one. Over the task, make sure that we change into single degree, which is our default. Click OK, and then we synchronize it. Do remember when you synchronize to reset the whole setting. Once it's done, click OK. Success. And let's see our chart. This chart is no much setting. Just click OK. And go to the filter. The filter is low pass. Set it to 50 Hz and butterworth. After that, we head on to the YT chart again, which is nothing much, and we go to the acceleration and time. Over here, just click OK, and we look to the statistic. In here, we change it from peak to peak. Yep, and that's where we get the list to find our decay rate. and then we run the whole data. After we run, we go to the acceleration time to see the point that we need to stop. As it's recording, we wait. And once it's there, we stop it. And then we click the clipboard over there, as shown, and we copy and put out it in the Excel. This is for eccentric A, and the other folder is for eccentric B. And as this is our result that we got. For eccentric mass A and eccentric mass B, we found our damping ratio, damp frequency, and also our natural frequency. And then we found out that our experimental and theoretical value is kind of big difference, so we plot the percentage out. That's all is how we get our data.
From the experiment, the eccentric mass with a higher polar moment of inertia has a lower natural frequency compared to the others. Decay rate is faster when the eccentric mass with lower polar moment of inertia is used in the experiment. The error between the experimental and theoretical value is large. Possible causes for this problem are improper setup of the experiment, calibration of accelerometer is not accurate, existence of unwanted noises in the signal. Therefore, random and systematic error must be avoided to get the accurate value in this experiment.
As conclusion, a method to investigate natural frequency and decay rate in torsional vibration system with 1 degree of freedom with variable eccentric mass was presented. The aim are achieved by changing the eccentric mass from a smaller polar moment of inertia to a bigger one. The natural frequency found from the analysis show that there are an error of 69.08% of eccentric A and 76.48% for eccentric B. The static deflection of eccentric A is larger than B as the J0 is smaller than B. The value between experiment and theory is larger because the random and systematic error occur in the experiment. Therefore, the experiment should be handled carefully so that the accurate result can be obtained.